So there we set the denominator equal to 0. Get plus or minus 2. These are points on my graph. These are vertical dotted barriers, right, that help me draw it. Next step is horizontal. All right, let's look at these degrees. The degree of the numerator and degree of denominator are the same, aren't they? The degree of the numerator, is it all right if I just put n is equal to d? In other words, I'm referring to the degrees here. Is that all right with you, everyone? Okay, they're equal, right? Haven't seen this? Haven't seen this? So the way we get this is a very special case. When we have this, what we're going to do is we're going to say y equals, so y is a horizontal line, y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Remember, the leading coefficient is the number in front of the highest power of x. So that means I'm going to take this number right here, 2, right? That's the top one, the leading coefficient of the numerator. And I'm going to divide that number. By the leading coefficient of the denominator, which is the one that's sitting in front of this x squared. And that's going to be right here. This is 1. So my horizontal asymptote is 2 over 1, which is 2. So that means that dotted line that we draw at the edge is not on the x-axis. It's up 2 units. So my magnet is up above. Does that make sense? Okay, that should be all we need before we're going to draw a picture. We're going to get our test points. How many test points will we have? 5. We should have 5 test points. 2 x-intercepts, 2 verticals. When it comes to test points, you don't worry about the horizontal. Okay, so it's these plus that. That's 4. We're going to need 5. But let's draw a picture, and I'm going to draw my picture over here. Okay. Give myself a little more space this time. All right, so I have x-intercepts at 5 and negative 4, and so I'm going to put way out here. Let me do it in blue. At 5, I'm going to put a point. And at negative 4, I'm going to put a point. Good. Okay, I have vertical asymptotes. I have 2 of them at negative 2 and positive 2. So at negative 2 over here, dotted barrier, positive 2, another dotted barrier. Okay, what next? I've done my x-intercepts vertical. I need this thing, right? This horizontal. So that's y equals 2. So what I'm going to do is at the ends only, I'm going to go up 2 units and I'm going to draw a dotted line. So if I went up, let's say here's 1, let's say here's 2, right? Out here at the edge, and when I say the edge, I mean go past the last piece of information you have. The last piece of information I have is negative 4, right? So I'm going to go past that, and over here I'm going to start drawing a dotted line this way. And then over here, the last piece of information I have is that I have an x-intercept at 5. So somewhere over here, I'm going to draw my dotted line. Y'all see that horizontal? Lifted up 2 units. Okay, test points. I will mention, you know how you asked about like how I can tell? The book does go into it a little bit. The ebook does talk about it. There is sort of like a multiplicity thing you can do. But again, it's, just testing the points is not that hard for us to do. It just takes a little time, but so would the other way a little bit. So, okay, test points. Step 6. Test points. We're going to have 6 of them. Wait, no, 5, right? It was 5? Yeah. So something to the left of negative 4. How about negative 5? I bet you could make a pretty damn good argument that this is going to come out to be positive. Why? Yeah, your magnet's up here, right? So you probably need to be up there to get up there, right? And if you were down here, wouldn't you have to go through the x-axis to get there? Okay, but who cares? I'm just going to still do the test point. All right, here, -3. So between these two pieces of information, I have a test point. And then between here and here, 0 is a good one, right? Always pick 0 if you can. Between here and here, 3 or 4, or could you use 3.29652? Yeah, whatever you want, right, between there. To the right here, 6 or 6,000, whatever you want. Hey, have you noticed that so far when we've had test points, you've always been able to find a nice whole number between the two things you're looking at, right? Like what if this was 2 and this was 3? Then you would have to pick something between 2 and 3, so it would have to be something like 2.5, right? I normally try and make my exams where those numbers are nice like this, and where you're not having to pick decimals, all right? All right, we're testing. We're going to plug these into the function. So -5 is going to go in, -3 is going to go in, 0 is going to go in, 3 is going to go in, and 6. All right, let's do one of these. So when I test -5, I'm going to test it right here. Okay? Now, 2 is always positive, right? 2 is always positive. And positive doesn't change the sign of anything. So I'm going to ignore the 2 completely. Okay, plug in -5 here. -5, take away 5. -10, right? So you have a negative there. Times -5 plus 4, negative. And then -5 plus 2, negative. -5, take 2 more away, negative, right? 2 negatives on top give you positive. 2 negatives on the bottom give you positive, and the ratio of 2 positive numbers is still positive.
You don't even have to check 3.
Pardon? You don't have to check what?
-3.
You don't have to check -3? Why?
Well, we know it's negative because it crosses through the x-axis.
It could bounce. Yeah, good. I'm glad you brought that point up. So we know this is going to be positive, right? But that does not mean that we have to be negative here, because you could come down and you could bounce off and go back up. It is possible. -3? No, I think it should be negative.
Negative on the bottom.
It should be negative.
That
Should we do it?
Negative and it multiplies to the other one.
Let's do it. -3 right here. -3 take away 5. -8. Okay. -3 plus 4. +1. Okay. And then -3 take away 2. -1. And then -3 take away 2. Negative, right? -5. So your top is negative. Your bottom is positive. The ratio of a negative and a positive is negative.
I messed up the bottom.
Yeah, I mean, look, if you're taking a test and you get one of these test points off, of course your graph's going to be wrong. But if that's all you do and everything else is right, of course you're going to get a lot of credit for the problem, right? But I would love to see like finished graphs that are right. Yes?
When you're checking, do you just ignore the 2?
I'm ignoring the 2 because we could have looked at that 2 right here as being a positive and sitting right here, right?
Oh.
And do you agree that a positive times a positive is still positive? And a positive times a negative will stay negative. So the positive 2 doesn't impact anything. If you wanted to, you could have put it there.
I'm just like, I want to know if like, it would affect anything like on a test if I don't.
If it was -2, it would,
Okay.
right? If it was -2, I would need to consider it, because then that would be a negative here as well, right? Which would change that to negative.
But when it's a positive.
When it's positive, you can ignore it.
And then if it's negative.
If it's negative, you need to keep factor it in. Take it into consideration. All right, so here, let me just give you the answers now, and these should again alternate. So this is plus, this is minus, this is plus. So now some dots, and then we draw a picture. So this is going to be a point where people are going to have like a little bit of a, like how do you do this? And I'll address it. Let me explain what I mean. At -5, you just know you need a point that's positive, right? I could put it here, Or 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 I could put it here, right? Just anywhere, right? Any of those. All of us are going to have different answers. None of these are wrong, all right? Any of these you can pick. But do you all see that if I pick a point up here, my graph's going to come down towards that, right? And if I pick a point here, it's going to come from the bottom up. Both of those would be correct on a test, all right? Because again, we're not too concerned about how we're getting to this, just that we are getting to it. And that over here, we are above the x-axis. That's it. So what do y'all want? Y'all want me to do one above or below, just for this? Below? You could even do it right on it, but then you just need to kind of come over and flatten out to it. You want me to go where? Above? Above? Below. Okay, so I'll do below for this one. Okay, so not below, it's above the x-axis, but below the green dotted line, right? So something like that. And then at -3, we're negative, so I'll put it here. At 0, we are positive, so I'll put it, I don't know, here. At 3, we are negative, I'll put it here. And how about for 6, which is positive, how about I put that one up here? Just so we can see a contrast of two different approaches, right? This one, I put it below the green. This one, I put it above. We good with this?
So you can't go above the green?
Yes. Remember, it's only the end behavior that's telling us about, right? All right, so I'm going to draw. Start with this point, come this way. Flatten out to this, right? Okay, connect the dots, kindergarten, right? From here to here, you're in kindergarten. I don't mean that to sound like insulting, you know what I mean? But it is, don't overthink it, is what I'm really trying to say. You're just connecting these dots, bless you. Now, from this point, you have to draw it this way, right? And we're going to have to go down because you can't turn up, right? You can't turn up because you would cross the x-axis here. So it's like a process of elimination. We know we must go down. This point right here is next, right? Going this way, barrier forces me up or down. Can't go down, right? Do I cross anywhere here? No, right? I have no x-intercepts here, so you can't come down. You're going to create an x-intercept, won't you? So you have to go up. This is a lot like the last problem. And then to the right, same thing. It's got to turn up again. Don't think that all problems have a little u in them. It doesn't always work out this way. It just happens to be the way this looks.
But it couldn't cross the horizontal asymptote.
Nope. What did I say about the horizontal asymptote? Only at the ends. That's why you don't draw it all the way across. And I think I even warned you last time that if you go to a tutor, they're probably going to draw it all the way across.
Yeah, I went to the tutor, that's what he
Did he draw it all the way across? Or yes, they did? Okay. Well, it's not their fault. That's the way it's taught. And that's the way you see it in books as well. But for me, why draw it all the way across? I mean, it is your end behavior, right? It's not telling you what's going on in the middle. And all it does is confuses you because you think there's a dotted line here you can't cross. So you think you have to go down, but then you can't go down. You're like, what the hell do you do, right? So then you just draw a smiley face, right? Or something like that and move on.
So it's easier this way.
Well, I think it makes more sense this way, which is the way I've always presented math to people is the way it makes sense to me, right? For some people that works, for other people they don't think the way I think, so it doesn't work for them, right? So, all right, here we go. This point, so I've moved to the next point, which is this one. Go this way, right? Down. Can't go up, no x-intercepts. So down, and then connect, and then, okay, well I put that point way up there, fine, I'll go to it, right? And then I'm going to have to flatten back out to this. So that little hump that I made may not be what that graph really looks like, but what I can tell you is to the right of 5, you are above the x-axis, and you flatten out towards 2. All right, shall we look at it?
So I thought you couldn't cross that green line, or
The green is only telling you what happens way out, right? So what, like, I don't think you would have had a problem with what I just did if I would have drawn this way out here, right? Then you would have said, okay, yeah, you go up and then you come down, you flatten out towards 2. So don't look, the red is a barrier. You can't cross it, right? The green is more of an idea of what's happening at the edges, all right? And you're allowed to fluctuate, okay? When you have, there's other functions in math where you have a horizontal asymptote that you cross infinitely many times. So let's say you have a horizontal asymptote like this, You can have a function that does this.
So this keeps approaching it constantly.
You can have a function that goes like that. Which means that the further you go out, the closer and closer. It's like it gets funneled in. Imagine there's like a funnel. There's this funnel that is like forcing your graph in between. It just keeps getting thinner and thinner and thinner and thinner.
It's like a sine graph of a circle. It's just getting smaller.
Yeah, this would be kind of like a sine. We call this a dampened oscillator. So it's oscillating, but it's also like dying out as it goes. Well, this way, sorry. It's dying out, which is realistic. Like in the real world, if like I take a ball and I drop it, right? I drop it, it comes up. It doesn't come back up to where I dropped it from, right? It comes up less high. Why? Lost energy. How did it lose energy? Heat. What was the heat? The deformation of the ball when it bounced. That movement was heat. That's loss of energy, so it can't come back up to where it was, and then it bounces again, loses energy again, keeps going, and eventually it stops, right? This is a model of that sort of behavior. Bounce, bounce, less bounce, and then it eventually tapers off to nothing. Okay, we're going on. Yeah, so that's the picture.
Vertical, you can't cross.
Can't cross, no matter what. Horizontal, you can cross, you just have to go towards them at the edges only. Okay, here's the picture of this one, just to see how we did compared to the computer. X squared, oh wait, it was 2x squared minus 2x minus 40 over x squared minus 4. And let me go to the standard graph, that's the way that Desmos would give it to you right there. If I just zoom out, I don't know, we kind of have this effect, don't we? We kind of have this effect. This kind of like funneling in with a little U in between. And hope it's obvious to you that when we go to the right, we have an asymptote. Let me type that asymptote in, y equals 2. Make it a dotted green. You'll see that dotted green? That's up at 2. See it's 2 there? Do you see that as I go to the right? We're getting closer and closer to it. Now, our graph doesn't do that, right? Our graph is a little different than that. That's okay. I've told you this from when we first started talking about polynomials, that our desire here is to not have this precise picture of the graph. We want a general picture of the graph, being pretty accurate where we can, and then as we go on into higher levels of math courses, we can use other tools to help us get all these fine details established. Yes?
So we're more concerned about validity than we are precision right now.
We're more concerned about where the graph hits the x-axis, right? Where the x-intercepts, where the graph has asymptotes, vertical asymptotes, right? We're concerned about where the graph is above and below the x-axis, and then the end behavior. That's it. We don't care about highest points, lowest points, any of that. We are being precise. Is that what you said? Say what you said again.
We are not concerned as much about precision as we are validity.
Okay. We are precise. We are being precise in the sense that I can tell you exactly where the x-intercepts are. I'm being precise in the sense that I can tell you exactly what the vertical asymptotes are, and precise in the sense that I can tell you exactly what the horizontal asymptote is, right? So I'm not losing precision. I'm just not trying to find every little detail of the function. That's all, okay? There's more details we can find. Now, where does this come into play? Like, where are you going to see this? In Cal 1, you're going to have problems where we do want to graph these in detail, all right? And the first step is to do this. You got to do this first, right? You got to have all this information first. Then you figure out all those little things. All right, third example, and I'm doing okay on time. So I hope this is helpful to you, that it's making a little more sense. All right, I was real concerned about time, so I wanted to make sure we could get through this one, and so the factoring is not going to be that bad on this one as well. There we go. That is a rational function. And for the first time, we have a problem where the degree of the numerator is bigger than the denominator, right? You'll see it? But we'll get to that when we get to it, right? We're not at that step yet. Let's just do step 1, which is to factor. Step 1, we factor. All right, factoring the numerator. What do you see? Pull an x, right? GCF first. So this is equal to x times x squared minus 25. Can you go any further? That's a difference of squares. So this is x times x plus 5, x minus 5. All right. I'd say that's factored. Next thing. Factor at bottom, right? Quadratic. Minus 3 plus 2. Not showing the steps for that, trusting that you could get that. And so now I'm going to come back up here and I'm going to rewrite this as x times x plus 5 times x minus 5 over, and then x minus 3 times x plus 2. Step 2. Holes. Don't forget holes. Do we have holes? No holes. No holes, right? Nothing cancels here, so no holes. Step 3, x-intercepts. Can you just tell me what they are? 0, 5, and negative 5, right? You're just setting the top equal to 0. So 0, 5, negative 5. The order of those don't matter. Step 4, vertical asymptotes. So set the denominator equal to 0. 3 and negative 2. Are we going too fast, or is this all right, everyone? Everyone okay? Yeah? All right, now, this is the fourth step. This is the step that's different, right? So for the fourth step, for my horizontal asymptote, what I have here is that the degree of the numerator, right, is bigger than the degree of the denominator. So I have the degree of the numerator is bigger than degree of denominator. And this is our final case. Think about this. In mathematics, we call this the trichotomy of numbers, meaning that if you give me two numbers, right? Give me a number, I'll call it x, give me a number y. Take those two numbers. We have this thing called trichotomy, meaning that this number is either bigger than this number is either less than this, or these numbers are equal. There's only three possibilities, right? This bigger than this less than this, or they're the same number. So when we're comparing the degrees to each other, there's only three possible outcomes, right? This is either smaller than this is bigger than this, or they're the same number. I've shown you two of the three cases, yes? This is the final one. So what happens here? What happens here is you have no horizontal asymptotes. You have no magnets. There aren't any, okay? There aren't any. There's no flattening out, which means that it acts like a polynomial function. Do you remember what polynomials did at the ends? That, and we use this test to see. I'm not saying we're going to use the test. What I'm saying is that the ends are either going to, this left end is either going to do that or that, and the right end is either going to do that or that. Okay? It's just no flattening. That's what I can say. We will still have to figure that out, but there's no little chart or table that we're going to use. All we're going to do to figure this out is just to use our test point. If our test point winds up being above, then we know it goes up. If our test point is down, we're going to go down. All right? Okay, let's do it. Step 5, step 5, I'm going to draw, oh wait, I feel like I'm missing something. We're on 6, so did I miss a step?
You did 4 twice.
Oh, I did 4 twice. I'm like, wait a minute, I'm confusing myself. Okay, thank you. I did step 4 twice. That was step 5. Now we're at step 6, which requires a little graph. I'll squeeze it in right here. Okay. All right, x-intercepts, -5, 5, and 0. So I'll do this in blue. So -5, 5, and 0. I have two verticals at 3 and -2. So -2, I have a vertical. And at 3, I have a vertical. And I have no magnets. Nothing to pull it down, right? Nothing to flatten out at the edges. What now? Test points. How many test points? 6, 7, 6, 10. What is it again? That plus that, there's 5, we need 6. So test points. All right, we need 6 of them. Something over here? -6, right? Between here and here? -4. Between here and here? -1. Between there and there? 2. Between there and there? 4. Life sucks. Okay, 6, right? We got all these things to plug in, right? So we need the function evaluated at -6. We need the function evaluated at -4. We need the function evaluated at -1. We got the function evaluated at 2. We got the function evaluated at 4 and the function evaluated at 6. You know what to do, right? At this point, just plug in positive or negative. Plug and chug. All right, so I believe if we plug in negative, we should get negative. We should get negative. Basically, I know that this number right here, I could have picked -60, right? And then it would have definitely made all of these negative. So if I had negative, 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 that's a total of 5 negatives. That would be negative still. So it's negative, and then yes, it does alternate again. It does switch. Not showing that work, right? And when we plug in -6, we get negative. So time to put some dots on this thing and finish it up, and we'll have one more example. And I'm ahead of schedule. So at -6, we are, what are we? Down, yeah, down, thank you. Down, and then at -4, we're up. At -1, we're down. At +2, we're up. And then down, and then up. Okay, that's kind of weird. So like I've done before, I'm going to start at the leftmost point that I see on my graph, which is this. And I'm going to draw that way, and then I'm going to draw this way. So when I draw that way, what? No magnets, right? No magnets, which means it has to act like a polynomial. So it's either going to go like this, up, or it's going to go down. What does it have to be? Down. Why not up? Because I would create an x-intercept, wouldn't I? I would have to cross the x-axis. Okay. So it's got to go down. So I'm just going to do this. Bye-bye. It's going down forever. Now what? Connect, right? Connect, and here's a barrier. Which way? Up. Yeah, because if you turn down, it's going to create an x-intercept. Here's the next point on my graph, moving from left to right. That way, what? Down, right? Because the barrier is going to force me down. So I'm going to go down. See, now I'm going to start doing this without drawing. I'm going to think it through first. It's going to go down here, connect, connect, and then what? Up. So I'm going to try and make it kind of look nice, like kind of smooth and there we go, something like that.
Do they always like curve?
Curve? What do you mean curve?
So on the left and right ends, there's no horizontal asymptote. Do they always curve down or up? They don't have a straight line.
They won't. It could be what we call these oblique asymptotes. The book covers these. I don't cover oblique asymptotes only because you don't need them through the rest of the calculus sequence. You don't really need oblique asymptotes. So you could some of these, what happens is that you have, not all of them, is that you can imagine a line like this, and it's curved but going towards the line. So it's almost like your horizontal asymptote gets tilted. And then you get closer and closer to it. But the graph will never be straight. This graph, even though it goes down, will never completely turn into a straight line. I think that's what you're asking, right?
Yeah.
Does it turn into a straight line? No. It will be curved. Okay, here, do y'all see it? These connect, right? These connect, and then I'm going to go down here. And then over here, it's got to either go up or down. Well, it can't go down because I have an x-intercept. It's got to go up. There we go. That's the graph.
Is that what you meant by the Y?
Yeah. So do you see the end behavior of these is like this, right? But how did we determine that? By looking at it and analyzing our test points, as opposed to using a table like we did for polynomials. All right, let me graph this one. So we've got x cubed minus 25x over x squared minus x minus 6. Let's go back to the standard graph. There it is. I don't know, ours is pretty good. I think both computer and us did a good job. Yeah? Our graphs look pretty similar. All right, last one. So before I do this last one, because I know I'm going to have time for it, one of the problems that I'm doing right now in my Cal 2 class is we're looking at a rational function, not that one, but we're looking at a rational function that does something like this. It has a vertical asymptote right here. And it has a horizontal asymptote that goes like this. And the function goes like this right here. And the function's doing other stuff over there, but what we're trying to figure out in the calculus class right now is what is the area underneath this graph. So think about that, because that's a little bit of a weird, strange problem, isn't it? Because would you agree that even though this gets smaller and smaller, it goes forever? It does, right? It goes forever. So there is area out here, right? Even if I'd have to zoom in, but I'd see a little bit of blue somewhere in there. And then this one goes like this, but there's also area. There's area there as well, right? It gets really thin, but it goes forever. And the area over here gets really, really thin, but it goes forever. So the question is, in the calculus class, is this area infinite? Like, is it an infinite area, or is it finite? And we're finding out that sometimes it's finite and sometimes it's infinite, and it depends on the function. So